Here's problem 3713. An interference pattern is produced at point P on a screen as a result of direct rays and rays reflected off a mirror as shown in the figure. If the source is 100 meters to the left of the screen, 1 centimeter above the mirror, and the source is monochromatic, wavelength 500 nanometers, find the distance y in millimeters to the first bright fringe. Here's our distance y. And our distance L is given. That's the distance to the screen. That's 100 meters. We have a source, and it's producing the direct rays and reflected rays. So there seems to be there's an image on the other side of the mirror that's producing this reflected ray. And so the distance between these two sources, if you will, if we were treating this similar to a double slit pattern, is going to be twice that distance to the mirror. So D is going to equal 2 times 1 centimeter, or 2 centimeters, 0.02 meters. Okay, we're also going to have a phase reversal of this ray that reflects off the mirror. This configuration is called Lloyd's mirror. And because of that phase reversal of the reflection, the y locations of our fringes is going to be reversed. In other words, our bright fringes are going to be located normally where the dark fringes would be for a two-slit pattern. So that's going to be equal to lambda L over D, m plus 1/2, where m is the order number. The first bright fringe will correspond to m equal to 0. So that will be our first bright fringe. So what is that? For the first bright fringe, we will have wavelength of 500 nanometers, 500 times 10 to the minus 9, times L, which is 100 meters, over D, which is 2 centimeters. And then we have the first bright fringe at order number 0 plus 1/2. So if I put all those numbers in, I get 1.25 times 10 to the minus 3 meters, or that would be 1.25 millimeters. So 1.25 millimeters up from the screen, we will see the first bright fringe, or up from the mirror itself, the first bright fringe, 1.25 millimeters.